Determine all intervals of concave up or concave down and determine the coordinates of all inflection points, including cliffs, for the function f of x equals cos squared x. The first thing to do is find the domain. F of x equals cos squared x, which means cosine of x first and then quantity squared. Cosine x is a trig function with no denominator. All terms are in the numerator here, so the domain will be all real numbers, or negative infinity to positive infinity. Trig functions have a tendency to have an infinite number of inflection points, if they have any at all, as well as an infinite number of intervals of concave up and concave down. But nicely, cosine x is 2 pi periodic, which means that it repeats itself every 2 pi radians. Another way to write this is f of x plus 2 pi equals f of x. So instead of working on the entire domain, which can be a little overwhelming, we can instead work on the unit circle interval, which starts at 0. It includes this, a square bracket, up to 2 pi. It does not include it's a round bracket, since 2 pi is the same point as 0 on the unit circle. We can find the results on the unit circle interval and extend them to the entire domain using the 2 pi periodic nature of cosine x. The next thing to do is find all candidate numbers. We need the second derivative for this. We will start with the first derivative. F prime of x equals, we will use the cosine x quantity squared version. It's a power rule. Bring down the power, leave the inside alone. Subtract 1 from the power, and then multiply by the derivative of the inside to complete the chain rule. Everything is multiplied here, so we can move it around in order. We can move the negative out with the 2. So negative 2. We can write the sine x first and then the cosine x. If we were to take the second derivative from here, this would require a product rule. But 2 sine x cosine x has an identity. It's equal to sine of 2x. There's a negative out in front of it, so it'll be negative sine of 2x. The advantage of writing it this way is it will make finding the second derivative easier, no longer a product rule, but also finding any candidate numbers will be easier. So it's probably advantageous to write it this way. It's now sine of 2x, and a sine of 2x is 2 pi divided by 2, which is pi, periodic. So it actually will now be under the condition of being pi periodic, which means it repeats itself every pi radians. Well, another way to write this is f of x plus pi equals f of x. So instead of working on the unit circle interval, we can now work on the interval starting at 0. It includes a square bracket up to pi. Does not include a round bracket. And we can extend the results to the entire domain using the pi periodic nature of sine 2x. We can now find the second derivative. There's a negative. The derivative of sine is cosine. Leave the inside alone. And then multiply by the derivative of the inside, which is a 2. That 2 can move out front with the negative, so it'll be negative 2 cosine 2x. We can now set the numerator and the denominator, if there is one, equal to 0 and solve for all x's. Let's start by dividing both sides by a negative 2. So cosine of 2x equals 0. So 2x is going to equal each of the places where cosine is 0. When we solve for x, we want the results to be in the interval from 0 to pi, but right now it's 2x, which means it's doubling that interval. So right now we need to work on the interval of 2 times 0, which is still 0, up to 2 times pi, which is 2 pi. So we need to work on the full unit circle interval to find 2x, and then divide by 2, and that'll put it in the interval from 0 to pi. cosine is equal to 0 in two places, pi over 2, and then again at 3 pi over 2 over the entire unit circle interval. We can now divide both sides by 2. This will put a 2 in the denominator of each of the terms on the right. 2 times 2 is 4, so it'll become pi over 4 and 3 pi over 4. Notice that each of these are in the interval from 0 to pi. They are therefore each candidate numbers. We can now draw an interval line, a line representing the interval. Which starts at 0, it includes it. It goes up to pi, it does not include it. So square bracket on the 0, round bracket on the pi. We can now put each of the candidate numbers on here in order. Pi over 4 is the lower of the two, and then 3 pi over 4, which splits the interval into 3 separate intervals. We can now pick a test value in each of these intervals. On the unit circle between 0 and pi over 4, there is only one angle in there. It's pi over 6. Between pi over 4, which is in the first quadrant, and 3 pi over 4, which is in the second quadrant, there's 3 different angles we can pick. The easiest would be pi over 2. And then between 3 pi over 4, which is in the second quadrant, to pi, there's only one unit circle angle in there, and it would be 5 pi over 6. We can now test the concavity by plugging each of these test values into the second derivative. We don't care about the value of the second derivative, just whether it is positive or negative. Starting with pi over 6, plugged into the second derivative, it'll give us cosine of 2 pi over 6, which can reduce to cosine of pi over 3. Pi over 3 is in the first quadrant, so the cosine will be positive. Then times the negative 2 will give a negative. We have a negative second derivative, which corresponds to concave down. Plugging pi over 2 in to the second derivative, we have the cosine of 2 times pi over 2. The 2's can cancel. It'll be cosine of pi. The cosine of pi is a negative 1, so we have a negative times the negative 2, which is a positive. We have a positive second derivative, which corresponds to concave up. Plugging in 5 pi over 6 into the second derivative, we have 2 times 5 pi over 6. The 2 and the 6 can cancel down, and it'll become 5 pi over 3. 5 pi over 3 on the unit circle is in the fourth quadrant, and the cosine in the fourth quadrant is a positive. So we will have a positive times the negative 2, which will make a negative. The negative second derivative corresponds to concave down. Now this left endpoint here is included. And this is pi periodic, which means this right endpoint overlaps with this left endpoint. And so this concave down interval here and this concave down interval here will connect together. So there's an interval to the left of 0 that will also be concave down that will connect to it. Notice that the width of this interval from 3 pi over 4 to pi, which is 4 pi over 4, is pi over 4 radians. So there's going to be an interval to the left of 0 of pi over 4 radians in width that's also concave down that will connect together to it. Well, pi over 4 radians away from 0 to the left of it is negative pi over 4, which means that we will have a full concave down interval starting at negative pi over 4 radians and continuing through 0 since it's included and all the way up to pi over 4 that we have here. This accounts for this interval as well as this interval because this one is repeated over here to the left of it. So both have been accounted for. So other than that, we have just a concave up from pi over 4 to 3 pi over 4. Right at the candidate number of x equals pi over 4, we have the concavity changing from concave down to concave up. So x equals pi over 4 will be an inflection point. It will have a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y will equal f of pi over 4. The original function is cosquared of x, which means to evaluate the cosine first and then square the results. Well, the cosine of pi over 4 is root 2 over 2, and then square the results. Root 2 squared is a 2, 2 squared is a 4, and the 2 and the 4 can reduce by 2 to become a 1/2. So it has a corresponding y-coordinate of 1/2. Right at the candidate number of 3 pi over 4, we again have the concavity changing from concave up to concave down. That will make x equals 3 pi over 4 also be an inflection point. And it will have a corresponding y-coordinate that can be found by plugging 3 pi over 4 into the original function, which is going to be cosine of 3 pi over 4, and then quantity squared. 3 pi over 4 on the unit circle is in the second quadrant. It's the pi over 4 equivalent. Cosine in the second quadrant is negative. Since it's pi over 4 equivalent, it'll still have the root 2 over 2 value, except being negative. Since it's being squared, it's going to become positive. Root 2 squared is a 2, 2 squared is a 4, and again, this can reduce to a 1/2. So it also has a corresponding y-coordinate of 1/2. There is the results over one interval. We can now make use of the pi periodic nature of the sine of 2x by adding to each of the x values here pi, the period, times n, an integer. For x values, each of the values in these intervals are x values. For the inflection points, just the x-coordinates are x values. The y-coordinates came from a trig function. So we will have concave down, negative pi over 4, plus the period times an integer, up to pi over 4 plus period times an integer. This will give all intervals of concave down over the entire domain of all real numbers. Concave up from pi over 4 plus pi times an integer up to 3 pi over 4 plus pi times an integer. And we'll have inflection points at pi over 4 plus pi times an integer, comma, 1/2, which will not have a pi times an integer because it's a y value and it came from a trig function of f of x equals cosquared x. And we have 3 pi over 4 also plus pi n and corresponding y-coordinate of 1/2 that will not get a pi times n, where here n is any integer. It can be a positive, it can be a negative, it can also be a 0. Plugging in n equals 0 will give the results over the interval we just worked on. And this will now give the results over the entire domain of negative infinity to positive infinity.